Thank you for your kind introduction. Hello, everyone. My name is Dong Zhou from Nanjing Tech University in China. My talk today is the localized damage behavior of welded joints based on plasticity method. I'm going to introduce my research in the following 4 parts. Firstly, please allow me to introduce my research group briefly. Our research group is founded by the academician Professor Santong Tu, and now the research leader is Professor Gong. In our research group, there are 3 professors and 3 associate professors, and there are 45 research students in total. And now we're working on the structural strength and light prediction, which is focused on the creep fatigue interaction problems and the structural integrity. And we're also working on the advanced design and manufacturing technology, like the surface hardening and the additive manufacturing, welding, residual stress control. And we're also working on the failure and protection of process equipment in complex environments, in which the material is under a molten salt and hydrogen environment. Okay, let's go on our topics. As we all know that the welded joints are very common in the engineering structures, from the aircraft to the ships, and from the bridges to the pipelines. And due to the inherent limitations, the welded joints is the weakest spot in the entire structure. So it's very important to investigate the damage behavior in the welded joint. Due to the rapid cooling and heating process during the welding, and this will result a very complicated microstructure. And this microstructure features can be easily taken into account by the crystal plasticity, like the grain orientations, different grain size, grain morphologies, and the hierarchical microstructures. The investigation on welded joints based on the crystal plasticity is very limited, both because they're very complicated microstructure, which may include many defects, but also for the competitive and multi-mechanisms like the dislocation slipping, twinning phase transformation, and avoids nucleation and their growth. Many research is focused on the local response, like the phase evolution in the heat effective zone or the plug initiation in the inner critical zone. The investigation on the entire welded joint is very limited because the crystal plasticity is really parameter dependent. So you have to identify the material parameters for each micro zones, like the base zone, welded zone, and the heat effective zone. And it sounds like it's impossible to test the mechanical response of the heat effective zone directly. Here, our test sample are cut from the P92 pipe, and according to the optical micrograph of our experiment materials, we can collect the micro information like the grain morphologies of different microzones, and we can obtain the grain diameter distribution, and then we can calculate the average grain diameter. And based on this information, we can establish our CPFE model as shown here. Because the pipeline system in the power plant is always under the condition that is under a high temperature, which is higher than 650 degrees. So the creep problem is very important and cannot be ignored. However, the traditional CPFE constituting model with the AF Harding law cannot capture the creep deformation during the stress welding. So that's why we modify this equation, and you can see the modified CPFE model can capture it very well. And here I'm going to introduce you some damage parameter, namely the fatigue indicator parameter. That is the accumulated plastic strain and energy dissipation. These two FIPs is very widely used in the CPFE simulation for fatigue problems, but this have some limitations I'm gonna introduce in the later. But the third one is our proposed FIP called net slip, which is the quantitatively description for the dislocation slipping. And we also extract the damage evolution for the 3 diameters during creep fatigue interaction loadings. And you can see here, during the dewelling process, there's no increment for the first two parameters, which means they can't capture the creep damage. That's why we can propose a new FIP here. This slide, I can show you how we determine the parameters in the weld joints. Firstly, we can conduct the tensile test or the cyclic test, in which the test sample is made from the base metal or from the welded metal. And theoretically, we can obtain the material parameters for HAZ if we have the mechanical response of the entire welded joints, and by adjusting the parameter for this one to match with the experiment one, then we can obtain the mechanical parameter for HAZ. And then we propose the optimization procedure to determine this parameter. Firstly, we have to set randomly set the material parameters for HAZ randomly and do the simulation. And then the MATLAB program will read the simulation results and it will compare with the experiment one and calculate the errors. And it will automatically adjust the parameters and do this loop again until the simulation matches the experiment's results very well. And this slide shows the result comparisons between the base metal and welded metal and the entire welded joint under low circle fatigue and creep fatigue interaction loadings. According to these figures, we can know that our proposed optimization procedure is very efficient. According to these figures, we can conclude at high temperature and low stress regime, the plastic deformation are very easy to accumulate at the HAZ. And that's maybe the reason why the failure location is always found in this part. And in this figure, we can see that the mechanical response of the entire welded joint is very close to the base metal. But however, the failure location is always found in the HAZ. So that means the effect of localized response in HAZ is more important. And this slide shows the damage distribution in an RVG mode, which is extracted from this pot. And we can see that the three diameters can predict the same slip bands, but also the same location with the most damage value, which verifies the consistency of our proposed FIP. And here, this figure shows the damage distribution captured by the accumulated plastic strain and the net slip. Here, I need to make it clear that the results captured by the P and the energy dissipation is very close, so I only show one of them in here. During the first circle, we can see that the damage is accumulated at the HAZ and the intersection area between the base metal and the HAZ. And actually, this area can be identified as the intercritical HAZ. And also, we can notice that the damage is accumulated along the green boundaries. And when the fatigue circle, we can see the distribution under the 10th circle, we can see the damages accumulated place transferred to the intercritical zone. And these two zones will be respond to the type 3 and type 4 cracking. And the results captured by the net slip shows in the first circle, we can see it also accumulated at HAZ zone. Here we're gonna see there's the positive value and negative value of the net slip, which is corresponds to the green is under a tensile stress state or under a compression stress state. So we can see at the first circle, they are equal, but when it turns to 10th circle, the tensile stress dominates the damage. And this big slide will show the results during the creep fatigue interaction loading, and these three were extracted during the dewelling period. And we can see that at the very beginning, during the dewelling, the damages were also accumulated at the HAZ, and then will be shown in the critical zone. And we also extract the damage along this pulse at the beginning and ending of the dewelling. And the area covered by this two line is represents creep damage, and we can see that the creep damage is accumulated in the HAZ and in intercritical down. This figure shows that the result under CFI loading for the first circle and 10th circle, it looks like the same. So we can conclude that the damage distribution is stable up to several circles. And all the damages are accumulated in the green boundary in the intersection areas. So the type 4 cracking is the main failure mode for the welded joint under CFI loading. And the damage is prior to accumulate at the green boundaries. Here's the conclusion. We propose the optimization procedure to identify the parameter for HAZ, and then we find the HAZ is the place for either for plastic deformation to accumulate, and then we find the type 3 and type 4 crackings are for fatigue loadings, and type 4 crackings are for the quick fatigue interaction loadings. Thank you.